A huge thanks to Brian for sponsoring this video. Good fellow mathematicians, welcome back to another video. Today, a very easy integral, namely the one from 0 to 1 of x squared d. It should be the other way around, right? X squared dx. This is looking kinda weird, but you know me. I wrote it out right. Yes, you can indeed integrate x with respect to x squared. And this is what we call in mathematics the Riemann-Stieltjes integral. It first arrived to me over on functional analysis, and we also built a bridge over to physics back in functional analysis. And this right here is a class of very interesting integrals, and at the end of the video I'm going to show you an easy procedure, you could say, to calculate integrals of that form, where this differential one form that we have at the very back is a continuously differentiable function. So definitely make sure to watch the entire video to get a grip of all the nifty little details that we cover here. And if you are interested in the graphical side of the Riemann-Stieltjes integral, why not check out the contents of today's sponsor print? More information at the end of the video, and now we are going to dive right in. So before we cover this integral right here, I would like to go back to the so-called Riemann integral. This is the one that we are used to. And before we get to that, we are going to take a look at the easier version, namely the integral from 0 to 1 of x integrated with respect to x. Now, most teachers say, well, this dx right here just tells you what you are integrating with, with respect to x, for example, but this is not the case. This differential one form that we have at the very back is actually really important, especially when you have something like the Riemann-Stieltjes integral, where this right here can be any random arbitrary function. Now, at first, I would like to take a look at the graphical interpretation of what the Riemann integral actually is. So if we take a look at this integral right here, from 0 to 1, then this right here is just the parent function f of x being equal to x. And what we want to do is we want to calculate the area under this curve from 0 to 1. How would you go about calculating this area? Well, using the integral or by using infinitely many little rectangles. So what we do in a normal case with a Riemann integral is we split up this interval that we have right here from 0 to 1 into n many equidistant partitions. So we are going to take, for example, 5 partitions here, 1, 2, 3, 4, 5. And with that, we can construct ourselves little rectangles that we can add up and get an approximation for the area under this curve. So this right here is going to be the first rectangle, then this right here is going to be the second rectangle, and so on and so forth. I think you know how that one works out. So by adding up those 5 rectangles, for example, you are going to get an approximation for the area under this curve. But how can we get an accurate approximation, like 100% accurate approximation of the area under this curve? Well, we are just going to make more and more partitions, meaning we are going to halve those partitions, once again 10 partitions. We are going to get a smaller and smaller error up here, and if we have infinitely many partitions, we are going to get an exact area under this curve. So if we have n many partitions down here, and those partitions have a length of delta x, so this little length right here is going to be called delta x, then we can actually get ourselves a formula for the Riemann integral on this certain interval. Namely, in general, we are going to take the limit as the number of partitions goes to infinity of, and what we are going to do is we are going to add, so the sum, all of our rectangles together, where I starts at 1 and goes to n, because we have n many rectangles, because we have n many partitions, obviously. And what we are going to do is we are going to take base times the height. The base is delta x, which is going to correspond to our infinitesimal that we have over here, dx, our differential one form. And what is the height exactly? The height is, for example, our function f of x evaluated at 1, or the function f of x evaluated at this spot right here. We are going to call this spot xi. So if we evaluate our function at xi and multiply it by dx delta x, and we add all of those together infinitely many times, we are going to get the area under this curve. Now we still have a few things in here which are pretty uncertain. Now f of xi, what is xi exactly? Let us take a look at how we can land at our xi here. Let us try to find an expression for our xi. Now xi is, we take the starting spot, our lower bound a, in our case this is 0. And how are we going to land at xi? Well, since all of those partitions are equidistant, so all are delta x apart, we can land at xi by just multiplying delta x by I, because if we take 4 times delta x, we are going to land at delta x, delta x, delta x, delta x. We are going to land at xi, and this right here would be x4, 1, 2, 3, 4, meaning our xi is 0, our lower bound, plus I times delta x. This right here is an expression for our xi, but this includes delta x yet again. What is delta x exactly? Now delta x you can define in different ways. What you can say is that delta x is if you have the xi member and you subtract from it the xi minus 1 partition, then obviously this right here is going to just give you the distance between those two, xi and xi minus 1. So that delta x is the same as xi minus 1. But this doesn't help us right now, because then this is kind of circular. Then you would have delta x just with respect to xi once again. This doesn't help in our case. So we need to get to delta x in some kind of different way. How can we get to delta x? Well, delta x is just our whole length of the interval, in our case 1 minus 0 or b minus a, divided by the number of partitions, namely n. So if we have 1 minus 0 and we have 5 partitions, then each and every delta x would be 1 divided by 5, which is 0.2 apart. So this is going to give us 1 over n, meaning our xi is going to be the same as I times 1 over n, or I divided by n. So meaning we can calculate the integral that we have up here as being the limit as n approaches infinity. I'm going to denote it as capital L, of the sum where I is bounded between 0 and n, of f of xi, in our case, xi is I divided by n, and f of x is nothing other than x. This is our function here, just going to be I divided by x. And delta x that we get right here is 1 divided by n. No, I divided by n, sorry, not I divided by x. And then you can start and calculate the stuff. Okay, so you have the sum where I runs from 0 to n of I. This is just little Gauss, n times n plus 1 over 2, and so on. And then you can calculate this very integral, giving you overall x squared divided by 2 from 0 to 1 is just 1/2. Okay, this right here is the regular Riemann integral, but now something is going to change for our Riemann-Stieltjes integral. Remember where we want to get. Namely, for the Riemann-Stieltjes integral, our differential 1 form, our infinitesimal, is dependent on some function g of x, where our g of x is x squared in our example here. The Riemann-Stieltjes integral basically is substituting this equidistant partition that we have down here for a nonlinear scaling, for example for a quadratic scaling, or maybe for a logarithmic scaling, or whatever you wish, or a fractional scaling. It really doesn't matter. Only thing you do is you scale it up in different proportions. Like for example, this one right here is going to just stretch in a parabolic manner, for example. This is everything that the Riemann-Stieltjes integral does. And the Riemann integral is just basically the linear version of that, where you have nice equidistant partitions, and that is easy. Remember, our delta x is the same as xi minus 1. Well, for the Riemann-Stieltjes integral, all we do is we substitute our differential 1 form for g of xi minus g of xi minus 1. And this is exactly the term which is going to give you a nonlinear scaling in the process. And now we can just plug this term, our delta x, nothing is going to change for the Riemann sum that we have right here, into here, and then we can calculate our Riemann-Stieltjes integral x integrate with respect to x squared. Let us do that and see where this is going to get us. So this is the limit as n approaches infinity of the sum where I is bounded between 1. Oh, I have written 0 here. I'm terribly sorry about that. I is bounded between 1 and n. Now f of xi. Our f of x is x. Once again, our xi's are I divided by n, so we are going to have that term once again. Multiplied this time by g of xi minus g of xi minus 1, where g of x is x squared. We still have our terms I divided by n. Okay, this is our xi, and our xi minus 1 is going to be I minus 1 divided by n. And all of this is going to be just squared, because this right here is the function that we are using. By the way, those functions are supposed to be real to real. Okay, so our g is a mapping from the real numbers to the real numbers. This is one of the restrictions for Riemann-Stieltjes integral to be a Riemann-Stieltjes integral. So we are going to get I divided by n minus I, and all of this squared, minus 1 divided by n squared. And this right here is our Riemann-Stieltjes integral. And now we can start to calculate further. This right here always works for each and every real valued functions, real to real function that you have over here in the differential form. Now we can start multiplying stuff out. That's the limit as n approaches infinity of our I. I'm just going to denote it with I. I divided by n. Now we're going to get I squared divided by n squared, and then we have negative. This right here is just a binomial formula. So I squared minus 2i, and then plus 1 divided by n squared. And now we can start to bring those fractions together. We can, in fact, factor out the 1 over n squared and put it to the front. That's limit as n approaches infinity over 1 divided by n cubed. N times n squared is n cubed times I. Now, what we still have here in parentheses, in brackets, is I squared minus I squared. This is going to cancel out, giving us in the process just 2i minus I. And this is where we stand at the moment. And now we need to start simplifying all of that a bit further. Obviously, we still have our summation. And now we can drag our I into here and break this summation up. It's a finite summation, so there's no restriction in breaking it up whatsoever. And giving us overall the limit as n approaches infinity of 1 divided by n cubed times. Now the first summation that we are going to have is where I is bounded between 1 and 0 of 2i squared, and then we have negative. I'm going to bring the 2 to the front. This really doesn't hurt either 2. And then we have I being bounded between 0 and n once again. So many indices, I'm terribly sorry. And now we have I here. As mentioned previously with the regular Riemann integral, if we sum up, and it starts from 1, if we sum up our I from 1 to n, this is just going to be little gauss that we get right here. So n times n plus 1 over 2. So just imagine you sum up 1 to 3. So 1 plus 2 plus 3. This is going to give you 6 in the process. Or with little gauss, you are going to have n. The number of members is 3, and 3 times 3 plus 1. So 4 is 12 divided by 2 is 6. So this checks out. And this right here is kind of a similar formula with just one more term. This can be comprised to, if you sum up all the I squares into n times n plus 1 times 2n plus 1 divided by 6. I think I made a video on that already, but I'm not certain. This is like a harder version of Gauss, you could say. It's the bigger Gauss, not the little Gauss. And now with that out of the way, we can start to multiply stuff out and just put some stuff together. Don't forget, we still have 2 as a factor here, and we also have n plus 1 times 2n plus 1. I'm going to make a little side calculation here. This is going to result in 2n squared. Then we are going to have 3n. And lastly, we have plus 1. And multiply this by n, we are going to have 2n cubed plus 3n squared plus n. Divided by 6, we also have a factor of 2 over here. All in all, we are going to get the limit as n approaches infinity of 1 divided by n cubed. We are going to get, on the first term, 4n cubed. Next up, we are going to get plus 6 n squared plus 2n divided by 6. And then we are going to get negative n squared plus n divided by 2. And let's think that's just a bit of algebra. We can bring those together. We can expand this by 3, giving us 6 in the denominator here. And overall, we are going to be left with the limit as n approaches infinity of n cubed. And then we are going to get a fraction where we can break it up into, we don't have a factor of n cubed anymore. So we are going to get 4 divided by 6 or 2 divided by 3, but with an n cubed. Next up, we are going to get plus. So we have 6n squared minus 3n squared is 3n squared. Divided by 6 is going to give us n squared divided by 2. And last but not least, we are going to get 2n minus 3n is negative n. So negative n divided by 6. And now we can bring our 1 over n cubed into here and see if we can cancel stuff out. So this is the limit as n approaches infinity. Now I'm going to write it out in the last step of n cubed and n cubed is going to cancel out, so we get 2/3 here. Then we have n cubed and n squared. We are going to be left with a 1 over n in some kind of way, so 1 over 2n. And here we are going to have a factor of n squared in the denominator, so negative 1 over 6n squared. And I think everyone can see where this is going now. When n approaches infinity, those are going to vanish, giving us in the process that the value of our Riemann-Stieltjes integral from 0 to 1 of x integrated with respect to x squared is going to yield 2/3. And that's a bit different from the regular 1/2 that we would get in a normal case if we were to integrate x with respect to x. Now this right here was just some hard abstract mathematics, and you can formalize this a bit more. Just like with the regular Riemann sums, you get upper and lower Riemann sums, and you get the same with the Riemann-Stieltjes integral. So you can take those rectangles from this perspective or the lower rectangles. Okay, if you take those rectangles and sum those lower ones up, and if the limit of those are equal, then you are going to get a Riemann-Stieltjes integrability. Now, there is an easier way to calculate stuff like this just with the regular Riemann integral. But this only works if and only if your function g of x is continuously differentiable. Continuously differentiable means if you have a function which, when differentiated, is continuous once again, then it's continuously differentiable. Obviously, the original function must also be differentiable. Otherwise, you can't differentiate it, obviously, not in the regular mathematical sense. If this is the case, if your function g of x is continuously differentiable, then you can turn the integral from a to b of f of x dg of x into the integral from a to b of f of x g prime of x dx. This right here is the magic formula for the Riemann-Stieltjes integral in the nicest case possible. And this obviously works for dx squared, where g of x is x squared, because this right here is continuously differentiable. If you differentiate it, you are going to get 2x out, and 2x is continuous and also differentiable once again. So we can apply this trick here, meaning the integral from 0 to 1 of x dx squared is the same as the integral from 0 to 1 of x times the differential of x squared, which is 2x dx. This right here is going to yield 2x squared, and if we integrate this, we are going to get 2/3 x cubed from 0 to 1. On 0 it's going to vanish, on 1 it's just going to be 2/3. And I leave it as an exercise to the viewer to figure out what the integral from 0 to 1 of, let's say, just cosine of x d sine of x is. Figure out at first if sine of x is continuously differentiable on set interval, and then see if you can use our little trick that we have right here. And if you did enjoy what you have seen today, maybe you will also enjoy the content of today's sponsor. Brilliant, to a kind of to sponsor yet another video here on this channel. To really understand what's going on here, I seriously invite you to try out the calculus courses over on Brilliant and their integration courses. They really give you a great understanding about Riemann sums and what is going on here exactly in a very visual and playful manner. Just take a look at any of those things that I'm going to show you here on screen right now. It doesn't matter what I show you, if it's out of their physics courses, or maybe it's out of their chemistry courses, calculus courses, etc. No matter what it is, you're probably going to say to yourself, man, that looks really clean and tidy. And it seriously is like that. They are just so good at transferring knowledge over to the users in the STEM field in such a unique manner that it just seems like magic. Like seriously, when I say it, I mean it. Brilliant with their nearly 70 interactive courses in all topics STEM gives you some of the best online learning content that you can find out there on the internet. And the repertoire of courses is just outright amazing. It's outstanding how much they already have available on their website and how good they are at what they are doing. It's seriously cool to see how students can use their website to learn something new about trigonometry, for example, today. It's not about learning the trigonometric formulas, the addition formulas for the sine and cosine. It's also about understanding the graphical side of things, how the unit circle works out to get those addition formulae out in the first place. It's not about learning the abstract stuff or just looking in a lookup table to see what the value of an integral is going to be. No, the visual understanding of the topics at hand is also something that you really need to learn in order for you to understand mathematics, physics, computer sciences, and all the other stuff in the first place. And I invite you to try it out today for completely free by using my link at the top of the description, brain.org/FambleMaths. 30-day free trial of amazing awesomeness. Try out the whole landscape for completely free over on Brain and see if it's something for you. And if you feel like this could turn into a long-term relationship between you and the services, then definitely make sure to make complete use of my link here down there in the description. And the first 200 people to do so get 20% off an annual premium subscription. Also, you can use some of my QR codes up here somewhere at the top. Doesn't matter. Check it out and see if it's something for you. You can really enhance your knowledge any day with their app on the go or maybe just at home. It's really going to help you in your studies. Doesn't matter if you're at high school or in university. They always got something up their sleeve for anyone out there. So check it out and support the channel this way. Thank you guys for watching. This concludes today's video and has been a long time since I wanted to make a video on the Riemann-Stieltjes integral. Let me know what you thought, and maybe the Dabo integral is going to be next. See ya.